Hey everyone, Morgan here. So we are on page 16 of the Bonding and Lewis dot lectures outline for AP Chem, and we're going to be talking about what is called the Born-Haber cycle. And you really don't need to know the name Born-Haber or Born-Haber cycle, okay? But you really need to know the concept behind it. Max Born and Fritz Haber, both fascinating individuals, and I strongly recommend you look them both up on Wikipedia. They developed this way of estimating what we're going to call the lattice energy for a compound, which is the energy released when two gaseous ions combine to form a solid. So in this example right here, I have Mg2 plus gas and O2 minus gas combine and form MgO solid. Now this is not something that we're going to be really good at measuring directly in a laboratory. Instead, we can approximate it using other things that we have measured previously. And it tells us an awful lot about the strength of the ionic bond between Mg2 plus and O2 minus, which is going to be incredibly useful when we talk about the liquid solid states. Okay, all of the solid states for ionic compounds, really the properties are dependent upon how big lattice energies are. So one thing you're going to notice here, that releases almost 4,000 kilojoules of energy. Now, how do we approximate it? Well, the first thing we do is we just start with the element in their standard states. So, Mg solid plus O2 gas. Now, we know to sublimate, or to turn the solid into the gas for magnesium, takes 150 kilojoules. We've measured that. Then, to turn the Mg into Mg2 plus, that's called ionization energy. And that is something that we've measured also. Then, to take the 1/2 O2 gas and turn it into O gas, that is actually the bond energy. Technically, we would have to say it's half the bond energy for a mole of O2, because it's 1/2 O2 to O gas. Then, to put the electrons on an oxygen requires some energy, and that goes up to O2 minus. Now, we also know the heat of formation for magnesium oxide, which is the heat released when 1 mole of a substance is formed from its elements in their natural states. That's -6O2. So that's our endpoint. So all of these took us up, and then we dropped down to there. And that gives us that release of almost 4,000 kilojoules. Now it's interesting. When we look at it for sodium, the numbers are drastically different. Okay? And you're going to notice that we do the same thing, basically sublimation for sodium, then ionization, and then the bond energy. But a difference here. Energy is actually released when we add an electron to fluorine gas. And then the lattice energy, okay, which goes from here to here, only ends up being about -923. Now let's round off, let's say -1,000. So let's talk about this in terms of Coulomb's law. Coulomb's law says the force of attraction between two charged particles is a constant K, don't worry about what the number is, times the first charge times the second charge divided by the distance between them squared. Now, for magnesium oxide, you have a 2 plus and a 2 minus. Mg is a 2 plus, O is a 2 minus. And for sodium fluoride, you have a +1 and you have a -1. Now, the differences in the distances between the ions exist. They're not exactly the same size. They're pretty close, but they're not exactly the same size. So D is basically the same in both of these, which shows you that this force is 4 times bigger than that force. So the 1,000 versus the 4,000 actually tracks really nicely. And what that starts to tell us now is that it's 4 times harder to separate a magnesium ion from an oxide ion than it is for a sodium ion from a fluoride ion. And that's going to have a lot of implications when we look at things like melting point, okay, boiling points, which is a rare thing for an ionic substance. Okay, in the next couple pages, we're going to look at some mathematical examples of this. This is Morgan. Thanks for tuning in, and I'm signing off.